Welcome! Today, we delve into a critical analysis of the rapid evolution of machine vision, focusing on the emergent capabilities of large-scale video models as zero-shot learners and reasoners. The central thesis of our analysis is that large-scale generative video models, much like large language models before them, are transitioning machine vision from task-specific tools to unified generalist foundation models. We are seeing emergent zero-shot capabilities in models like VO3. Specifically, we found three key results. First, VO3 successfully solved a wide range of tasks, over 69 qualitative and quantitative tasks for which it was not explicitly trained. Second, based on its ability to perceive, model, and manipulate the visual world, VO3 demonstrates early forms of chain-of-frames visual reasoning, such as maze and symmetry solving. And third, we observe a substantial and consistent performance improvement from VO2 to VO3, indicating a rapid advancement in this field. Video models are zero-shot learners and reasoners, continuing with our methodology. Our approach is simple. We prompt VO. This minimalist strategy mirrors the paradigm shift in NLP, leading to our first key takeaway. Prompting is replacing task-specific training or adaptation in machine vision. Now, please direct your attention to Figure 1, a qualitative overview of VO3's zero-shot abilities. This plot maps VO3's success rate across 62 tasks spanning the entire vision stack, organized into 4 hierarchical capabilities: perception, modeling, manipulation, and reasoning. These categories build upon each other, providing a framework for understanding the emergent visual intelligence we are observing. We use VO3 because it has consistently ranked high on text-to-video and image-to-video leaderboards, and we compare it to its predecessor, VO2, to gauge the rapid pace of improvement. 3. Qualitative results. Sparks of visual intelligence. Figure 2 provides concrete examples of VO3's zero-shot learning and reasoning, ranging from classic perceptual tasks like super-resolution to complex visual reasoning tasks like rule extrapolation. We define success rate as the fraction of 12 generated videos that solved the task, providing a ballpark estimate of capability. Focusing first on perception, we see that without any task-specific training, VO3 can perform a wide range of classic computer vision tasks, including edge detection, segmentation, and interpreting ambiguous images like the classic Dalmatian illusion. Apart from denoising, none of these tasks were explicitly trained for in video models. This leads to takeaway 2. VO3 shows emergent zero-shot perceptual abilities well beyond its training task, suggesting that video models will likely replace most bespoke models in computer vision. Moving up the hierarchy, we examine modeling, intuitive physics, and world models. VO demonstrates a grasp of physics, modeling rigid and soft body dynamics, buoyancy, and optical phenomena. Crucially, it also understands abstract relationships and maintains memory of the world state. Next, manipulation, editing, and imagination. Building on perception and modeling, VO3 can meaningfully manipulate the visual world, performing zero-shot image editing tasks like style transfer, inpainting, and generating novel views. This ability allows it to plausibly simulate complex interactions. Finally, visual reasoning across time and space. We argue that frame-by-frame video generation parallels chain of thought in language models, which we call chain of frames, or COF. This enables VO to tackle complex visual problems, requiring step-by-step reasoning, such as graph traversal, sorting numbers, and maze solving. Takeaway 3 summarizes this. Frame-by-frame video generation parallels chain of thought in language models, enabling reasoning across time and space. 4. Quantitative results. Following our qualitative exploration, we now provide a quantitative assessment across 7 select tasks, focusing on perception, manipulation, and reasoning. We evaluate performance using both the best frame, the performance ceiling, and the last frame, which is predetermined and more practical. We also benchmark against the state-of-the-art image editing model, Nano Banana. Please look at Figure 3 detailing edge detection performance. We are measuring OIS performance as a function of K attempts. Notice the substantial performance increase from VO2 to VO3. On the left, the best frame plot shows VO3 achieving a pass at 10 rate of 0.77. On the right, the last frame plot shows VO3 matching Mano Banana's performance at 0.74. This zero-shot capability is remarkable, even if it doesn't yet match task-specific SOTA, demonstrating VO3's strong and generalizable zero-shot learning ability. Next, Section 4.2, Perception Segmentation. We asked the models to segment all distinct objects without specifying category or location. Figure 4 shows the results using mean intersection over union. Observe that VO3 achieves an MIOU of 0.74, comparable to Nano Banana's 0.73. This confirms remarkable zero-shot segmentation abilities, though we note that prompt engineering, such as using a green background, significantly impacts performance. Moving to Section 4.3, Manipulation, Object Extraction. We tested the model's ability to perceive and extract objects, lining up animals in a row. Look at Figure 5. While VO2 performs around chance, VO3 achieves up to 92% pass at 10. This rapid advancement in a simple manipulation task underscores the consistent performance improvement we are seeing across the board. Section 4.4 covers manipulation, image editing. We used human raters to evaluate fidelity, the correctness of the edit, and precision, the correctness without unintended changes. Figure 6 shows an example edit and the human rating results. VO3 especially excels in preserving details and textures. Look at the bar chart on the right. VO3 achieves 100% fidelity and 60% precision, significantly outperforming VO2. This suggests that with better control over unintended changes, video models will become highly capable 3D-aware editors. Finally, Section 4. 5. Reasoning, maze solving. This tests planning in a constrained environment. Figure 7 presents results across various grid sizes. Focus on the 5x5 grid chart on the top left. VO3 achieves a pass at 10 rate of 78% compared to only 14% for VO2. Crucially, while Gemini 2.5 Pro performs well when given the maze as text, it generally struggles when the maze is presented as an image, highlighting the advantage of solving a visual task step by step in a visual medium. We continue with Section 4.6, Reasoning, Visual Symmetry Solving. This task assesses the ability to understand and apply spatial reasoning. Figure 8 shows results for both shapes and random patterns. VO3 significantly outperforms both VO2 and Nano Banana. For the shape split, VO3 achieves 88% pass at 10 for the best frame. We also used this task to analyze prompt sensitivity, finding a 40 percentage point difference between the best and worst prompts, underscoring the importance of prompt engineering. Lastly, Section 4.7, Reasoning, Visual Analogy Completion. This tests abstract reasoning by requiring the model to understand transformations and relationships. Figure 9, summarized on the next page, shows that VO3 correctly completes examples for color and resize transformations, but struggles with reflect and rotate analogies, indicating systematic biases that still need to be addressed. Figure 9 details the visual analogy solving results. Note the high success rates for color and resize transformations, reaching 95% and 68% respectively, for VO3. However, performance drops significantly for reflect and rotate transformations, indicating an area for future improvement. This leads to takeaway 4. While far from perfect, VO3 shows emergent visual reasoning abilities built upon its capacity to perceive, model, and manipulate objects. In summary, our findings confirm that machine vision is on the cusp of a paradigm shift, mirroring the rise of LLMs. VO3 spans the full vision stack, from perception to visual reasoning. We must remember that the performance reported here is a lower bound on the model's true capabilities, as prompt engineering is crucial. While video generation is currently expensive, the economic trajectory suggests costs will fall rapidly, just as they did for LLMs. Although VO3 is currently a jack of many trades, master of few, compared to specialized SOTA models, the step change in performance from VO2 to VO3 is evidence of rapid progress. This rapid progress is further supported by our scaling results, which show pass at 10 consistently higher than pass at 1, indicating that inference time scaling methods and post-training optimization will likely boost performance significantly. VO3 is akin to a pre-trained language model that has yet to undergo instruction tuning. Our outlook is clear. We anticipate the same transformation seen in NLP, the GPT-3 moment for vision, will happen in machine vision, enabled by the emergent zero-shot abilities of video models to perform a broad variety of tasks, from perception to visual reasoning. Thank you for your attention. We are now open for questions.